Welcome to The Deep Dive. We've got this fascinating resource today. It's a general glossary, just packed with fundamental terms.
It really is quite something.
Yeah, and our mission really is to explore this glossary, pull out that core knowledge, the surprising bits and the essential building blocks that, well, they underpin so many technical fields.
Like laying a solid foundation.
Exactly. Supercharging your foundational understanding. Okay, let's just jump right in. We're starting with some physics and basic math concepts.
Sounds good. Physics and math, they're definitely the place to start. Let's take absolute humidity and relative humidity.
Okay.
So the glossary points out absolute humidity is the actual measurable amount of water vapor in a given volume of air. Straightforward quantity.
Right, the raw amount.
But then relative humidity, that's different. It's a ratio. It compares the amount of water vapor actually present to the maximum amount the air could hold at that specific temperature and pressure.
Ah, okay. So absolute is the what is there. Relative is how full the air feels with moisture compared to its total capacity.
Precisely.
That makes sense. Because you could have, say, warm air holding quite a lot of water vapor in absolute terms. But the relative humidity might still feel low because that warm air can hold so much more, potentially.
Exactly. And the glossary notes, quite rightly, that both are important, just in different contexts.
Like meteorology versus engineering.
Yeah. Meteorologists might track absolute humidity for understanding large-scale moisture transport, atmospheric stuff. But an HVAC engineer designing an office system, they're probably much more focused on relative humidity for human comfort and preventing condensation.
Right, avoiding damp walls or mold. It mentions deserts, too, even with low relative humidity. The absolute humidity can sometimes be surprisingly high.
That's a great point. It can really affect things like equipment preservation in ways you might not expect.
Okay, moving on. Pressure. We have absolute pressure, defined here as gauge pressure plus atmospheric pressure, often in Stebsal, pounds per square inch, absolute.
Yeah, the key thing here is the zero reference point. Gauge pressure, like your car tire gauge, measures pressure relative to the surrounding atmosphere.
So it reads zero out in the open air, usually.
Right. But absolute pressure uses a perfect vacuum as its 0 point. So the zero gives you the total full pressure value.
Okay, so if my tire gauge reads, say, 32 psi, the absolute pressure is that 32 psi plus whatever the local atmospheric pressure is, maybe around 14.7 psi at sea level?
Roughly, yes. So you'd be looking at about 46.7 psi in that case.
It really shows gauge pressure is convenient for everyday stuff here on Earth, but absolute pressure is the full physical reality.
Couldn't have said it better.
Now, temperature. Similar concept here with absolute temperature measured relative to absolute zero. And it mentions Kelvin and Rankine scale.
Exactly. Absolute zero. That theoretical point where all molecular motion just stops. It's incredibly cold, minus 273.15 Celsius or minus 459.67 Fahrenheit.
Wow.
And the Kelvin scale uses that absolute zero as its starting point, 0 Kelvin, but it uses the same degree size increments as Celsius.
Okay. And Rankine.
Rankine does the same thing, but it starts at absolute zero and uses the Fahrenheit degree size. So 0 Rankine is also absolute zero.
It really makes you think, doesn't it? Celsius and Fahrenheit feel so, tied to water's freezing and boiling points, our environment.
They are very Earth-centric, yes.
Whereas Kelvin and Rankine feel more fundamental, linked to the basic physics of heat itself. The idea of absolute zero, it's still kind of mind-bending.
It is a theoretical limit with profound implications.
Okay, shifting gears slightly. Acceleration due to gravity. It lists the value as approximately 32.2 feet per second, or feet per second squared, here on Earth.
A real cornerstone of classical mechanics. It basically means ignoring air resistance.
Which we often have to.
Hey, indeed.
Yeah.
Ignoring that, an object's downward speed increases by 32.2 feet per second for every second it falls.
Pretty constant pull.
Well, mostly constant. It actually varies slightly depending on where you are on Earth. Altitude, latitude, even local density variations in the crust can change it just a tiny bit.
Really? So it's not perfectly 32.2 everywhere?
Not absolutely perfectly. These small variations are even important for things like high-precision mapping, geodesy.
Huh. Interesting. Still, it governs so much, from dropping keys to, well, flight paths. Okay, now some very basic math stuff. Addition, subtraction, multiplication, which it defines as repeated addition, and division.
The fundamentals.
Yeah, and it lists the terms. Dividend, divisor, quotient, remainder, sum, difference. It seems almost too basic, but it's the bedrock, isn't it?
Absolutely. You can't build the complex structures without these foundations. And defining multiplication as repeated addition is key to understanding how it relates to other operations, like division being its inverse.
Right, and then it introduces algebra, using symbols for numbers.
Which is the big leap, really. Moving from concrete calculations with specific numbers to using symbols like X or Y to represent any number.
That allows us to generalize, right? To find patterns and solve for unknowns. Essential for engineering, science, pretty much everything.
Couldn't do modern science or engineering without it.
Okay, great foundation laid. Let's transition now into concepts more specific to aviation and engineering. First up, advisory circulars, or ACs, from the FAA.
Ah, yes, ACs. Very important. As the glossary says, these are non-regulatory. That's key. They don't have the force of law.
So not rules you have to follow.
Not legally binding in themselves, no. But they provide guidance, information, best practices, acceptable methods for complying with the actual regulations.
Okay, so they're like the FAA's official recommendations on how to do things properly.
That's a good way to put it. Following them often represents the agency's preferred way and can definitely smooth out approval processes. They're highly valuable.
Got it. Valuable guidance, not strict law. Next, aircraft specifications, described as FAA record-keeping documents for aircraft type certification.
Right. These are essentially the master documents for a specific aircraft model. They contain the official design data, operating limitations, things like maximum weight, engine type, required equipment.
The official blueprint and stats.
Exactly. They form the basis for determining an aircraft's airworthiness from a design perspective.
Okay. Which leads us naturally to the airfoil. The glossary explains it as any surface designed to get a useful reaction, mainly lift, from air moving over it, using Bernoulli's principle or Newton's laws.
The heart of how wings work. Bernoulli's principle is the classic explanation. Air flows faster over the curved top surface of the wing.
Longer path, same time.
Right. Faster air means lower pressure on top compared to the higher pressure underneath, creating an upward force lift.
Makes sense.
But that's not the whole story. Newton's third law is also crucial. The airfoil deflects air downwards.
Action-reaction.
Exactly. For every action, there's an equal and opposite reaction. The wing pushes air down, and the air pushes the wing up. For many airfoils, especially at lower angles of attack, this downward deflection of air is actually the dominant source of lift.
Oh, interesting. So it's both the pressure difference and actively pushing air down.
It's a combination, yes. The relative importance can vary, but both play a role.
Okay. Now, an airworthiness certificate. This is a required document stating the aircraft meets its type design and is safe to operate.
Absolutely essential. It's like the aircraft's registration and proof of fitness rolled into one. It confirms it was built according to the approved specs and has been maintained in a safe condition.
Can't legally fly without one.
Correct. No valid airworthiness certificate, no flight, period.
And speaking of safety, Airworthiness Directive, or AD. The glossary stresses compliance is mandatory, issued by the FAA for unsafe conditions.
ADs are serious business. Think of them as mandatory safety recalls for aviation. If the FAA finds a design flaw or a potential hazard in a specific type of aircraft, engine, propeller, or component...
Like a manufacturing defect showing up later.
Exactly, or maybe an issue discovered through service experience. They issue an AD that requires specific inspections or modifications, and owners must comply within the specified time frame.
Mandatory fixes. Critical for ongoing safety. Okay, changing materials now. Alclad aluminum. An aluminum alloy core coated with pure aluminum.
Now, for corrosion resistance. The strong aluminum alloys used for aircraft structures are great for strength to weight, but they can be susceptible to corrosion.
Right.
Pure aluminum, however, is naturally much more resistant to corrosion. So Alclad involves bonding a very thin layer of this pure aluminum onto the surface of the stronger core alloy.
So you get the strength of the alloy, but the protection of the pure aluminum layer.
Precisely. Best of both worlds for aircraft skin and structures. A clever materials solution.
Definitely sounds like it. Now, related to manufacturing precision, allowance, and tolerance, how do these differ?
Good question. They often get confused. Allowance is the intentional difference designed between the dimensions of two mating parts. It determines the type of fit, like a clearance fit where there's a gap or an interference fit where they press together.
Okay, so allowance is about how two different parts are designed to interact.
Yes. Tolerance, on the other hand, is the permissible variation in the size of a single part during manufacturing. No manufacturing process is perfect, so tolerance defines the acceptable limits the maximum and minimum size that part can be and still be considered acceptable.
Ah, I see. Allowance, planned gape overlap between parts. Tolerance, acceptable manufacturing error range for one part.
You've got it. Allowance is by design for fit. Tolerance is about manufacturing reality.
Makes sense. Back to aluminum treatments, alloydizing, a chemical treatment for corrosion resistance and paint adhesion.
Correct. It's a chemical process that creates a conversion coating on the aluminum surface. This thin coating chemically changes the surface, making it more resistant to corrosion and also providing a much better surface for paint to stick to.
So it protects the metal and helps the paint last longer.
Exactly. Improves durability all around.
Okay. Then we have alteration in the aircraft context. Any change from its original or previously altered state?
Pretty straightforward definition. If you change anything on the aircraft from how it was originally certified or how it was after a previous approved alteration, that's an alteration.
Like installing new radios or changing the engine type?
Yes. And significant changes, called major alterations, require formal approval from the FAA, often documented on a specific form, the FAA Form 337.
Right. More paperwork and scrutiny for bigger changes. Makes sense. Good. Fundamental electricity. Alternating current, AC, versus direct current, DC.
Big difference here. DC, direct current, flows in only one direction. Think batteries positive to negative.
Steady flow.
Right. AC, alternating current, periodically reverses its direction of flow. It cycles back and forth, typically 50 or 60 times per second in power grids.
Like the power from a wall socket.
Exactly. AT is used for large-scale power distribution because its voltage can be easily stepped up or down using transformers, which is very efficient for long-distance transmission. Aircraft actually use both AC and DC systems for different purposes.
Okay. And measuring that flow, an ammeter, measures electric current in amperes.
Yep. An ampere, or amp, is the unit measuring the rate of electron flow, how much charge is passing a point per second. The ammeter is the instrument you use to measure that flow in a circuit.
Got it. Now, a metal treatment process. Annealing, heating, holding, then cooling a metal. What's the goal?
Usually to make the metal softer, more ductile, meaning it can be stretched or drawn out without breaking, and to relieve internal stresses built up during manufacturing processes like rolling or forging.
So making it less brittle and easier to work with.
Exactly. It modifies the metal's internal crystal structure to achieve those properties, critical for many manufacturing steps.
Okay, back to aviation maintenance. The annual inspection, required every 12 months for most general aviation planes.
A cornerstone of maintaining airworthiness for smaller aircraft, it's a very thorough top-to-bottom inspection covering the airframe, engine, propeller, systems, everything.
And it has to be done by someone specific, right?
Yes, it must be performed by an FAA-certified airframe and power plant mechanic, an AMT, who also holds an inspection authorization, or IA. That IA signifies a higher level of experience and authority.
So a really comprehensive checkup by a qualified expert every year.
That's the idea. Essential for safety.
Then we have anodizing, another surface treatment for aluminum, specifically non-clad aluminum, using an electrolytic process. How's this different from alloydizing?
Both aim for corrosion resistance, but the process is different. Alloydizing is purely chemical. Anodizing is electrochemical.
Meaning electricity is involved.
Yes. The aluminum part is made the anode in an electrolytic bath, and passing current through it builds up a thicker, harder, and very durable layer of aluminum oxide on the surface.
More heavy-duty protection than alloydizing.
Generally, yes. It's very effective, especially for non-clad alloys, and you can also dye the oxide layer during the process to give it color, so it can be decorative too.
Okay. Back to AC circuits. Apparent power. Products of RMS voltage and RMS current in volt amperes, VA. What does apparent mean here?
It's because in AC circuits with components like inductors or capacitors, the voltage and current waveforms might not be perfectly in sync. They can be out of phase.
Okay.
Apparent power, measured in VA, is simply the voltage times the current, ignoring this phase difference. It represents the total power that appears to be flowing in the circuit, but the actual power doing useful work, called true power or real power, measured in watts, can be less than the apparent power because of that phase shift.
So apparent power is like the total electrical load the system sees, but only some of it might be doing actual work.
Kind of, yes. Think of it like beer in a glass. The apparent power is the whole glass, including the foam, but the true power is just the liquid beer you can actually drink. The ratio between them is the power factor.
Okay, that analogy helps. Now, a classic physics principle.
Her.
Archimedes' principle, about buoyant force.
Ah, yes. The old eureka moment. It states that the upward buoyant force on an object submerged, fully or partly, in a fluid is equal to the weight of the fluid that the object displaces.
So if an object pushes aside water, the water pushes back up with a force equal to the weight of that displaced water.
Exactly. And if that upward buoyant force is greater than or equal to the object's own weight, the object floats.
That's why huge steel ships float. They displace an enormous weight of water.
Precisely. It's all about displacing a weight of fluid equal to your own weight.
Simple, yet profound. Then, very straightforward one, area. Measure of a two-dimensional surface.
Absolutely fundamental. Square inches, square meters. Essential for calculating things like wing surface area for lift, pressure distributions, material quantities, countless applications.
You can't do much engineering without calculating area. Now, in aviation, weight and balance, ARM. The horizontal distance from a reference datum line to an item's center of gravity.
Crucial for aircraft stability and control. The datum is an imaginary vertical line set by the manufacturer. Could be the nose, the firewall, anywhere fixed. The arm is the leverage distance of any weight. Fuel, passengers, cargo, the engine itself from that datum.
Like a lever.
Exactly. You multiply the weight of an item by its arm to get its moment. Sum up all the weights and all the moments, and you can calculate the aircraft's overall center of gravity. It needs to be within specific limits for safe flight.
So arm is the distance. Moment is the turning effect of the weight at that distance. Got it. Next, armature. The rotating part of an electric generator or motor where EMF is induced.
That's right. In a motor, the armature has windings that carry current. When this current interacts with the magnetic field, usually from stationary field coils or magnets, it creates the torque that makes the armature rotate and do work.
And in a generator?
In a generator, it's the reverse. Something external rotates the armature within the magnetic field. This movement induces an electromotive force, EMF, or voltage, in the armature windings, generating electricity. It's the core component where energy conversion happens.
The active moving part. Okay, back to wings. Aspect ratio. The ratio of wingspan to the wing's average chord width.
A really important aerodynamic design parameter. It describes how long and skinny or short and stubby a wing is.
Does it affect performance?
Hugely. High aspect ratio wings, long and thin, like on a glider, are generally more efficient aerodynamically. They produce more lift for less drag, especially at lower speeds.
And low aspect ratio.
Yeah.
Short and wide.
Like on a fighter jet. They tend to be better for high-speed flight and maneuverability and structurally stronger, but less efficient in terms of lift-to-drag ratio compared to high aspect ratio wings.
Yeah.
So it's a trade-off based on the aircraft's mission.
Design reflects purpose. Makes sense. Then assembly drawing shows how all the parts fit together.
Yeah, this is a type of technical drawing. It's like the instruction manual picture showing the complete product and how all the individual components are oriented and connected to each other. Essential for putting things together correctly and for maintenance.
The big picture view. Okay, finally for this first big sweep. The atom. Basic unit of matter, protons, neutrons, electrons.
The absolute foundation of chemistry and material science. You have the nucleus at the center with positively charged protons and neutral neutrons.
Where most of the mass is.
Right. And orbiting that nucleus are the negatively charged electrons. The number of protons defines the element, and the interactions of the electrons determine pretty much all chemical behavior.
Wow. We really covered some ground there. From humidity and pressure all the way down to atoms and up to aircraft specifics.
It's quite a range, isn't it? And what's fascinating is seeing the connections. Basic physics principles underpinning engineering solutions, mathematical concepts needed for precise manufacturing.
Yeah, understanding pressure differences helps understand airfoils. Understanding materials like alclad helps understand aircraft construction.
Yeah.
It all links together.
It really does. These fundamental terms aren't just definitions, they're the building blocks for understanding complex systems.
So for everyone listening, hopefully this deep dive into just a slice of this glossary has maybe reinforced some things, clarified others, and shown how these core ideas form a really solid base.
It's like sharpening the tools in your mental toolkit, right?
Yeah.
Having a clear grasp of these fundamentals makes tackling more advanced topics much easier.
Absolutely. So maybe the final thought here is to consider, well, how interconnected everything is. Think about how Archimedes' principle applies not just to ships, but maybe to buoyancy in fuel tanks, or how understanding AC power relates to aircraft electrical systems.
That's a great point. Reflect on how these basic concepts, pressure, temperature, materials, basic forces, electricity, might echo or connect within your own areas of interest or work. Sometimes revisiting a fundamental idea can spark a completely new insight or a different way of looking at a problem you're dealing with. How might these basics unlock something new for you?